So I'm going to start with our next lesson entitled Soil Water. So in this chapter, we're going to learn what are the pores that we have learned previously, like for example, micropore, mesopore, and also macropore, and also the connection with the soil water. This is more towards the possible interaction based on different pore size and also their tendency to retain water. As you know, water is important for plant growth, especially for the process of photosynthesis. And that is why having water in the soil is crucial because that is the basis of life, to sustain life. Okay. So, as I've told you just now, why water is so important. Number one, photosynthesis by plants. Now, plants needs to absorb water for its photosynthesis when there are daylight. Now, after that, what is the next important part about water is beyond that. It can also cover the well-being of any life form. So apart from plants, water also is needed by soil organism. I'm not talking just about microorganism. I'm talking about whatever that lives in soil. That includes insects. That includes mammals that also live on nearer to the surface. So everything that requires oxygen, everything that also like living things, they will require moisture from the soil in order for cooling purposes or maybe for absorbing nutrients coming from various source, yeah, including from the soil itself. Okay, now it influence also the properties of the soil. Now, as you have learned before from what you've submitted in your lab report yesterday, most of you have already identified that having moisture in the soil will affect its texture, which is true. So I think you probably know the importance of texture. Too sticky, not good. Too sandy, too loose, also not good. So having water in the soil will definitely help, but too much is bad. Now, apart from that, is that due to the cycles of watering, wetting, and drying, it also will going to cause the swelling and also shrinking of the soil texture, especially when we're talking about clay. Clay very absorbing in terms of water. But if they don't have water and if they dry extensively, they turn back into stone-like and very hard structure, clay aggregate. So water, they are important in terms of the physical properties as well. Yeah? Apart from the give me a moment. Right. So this is the structure of water, and I don't think I'm going to explain to you. Everybody knows H2O, the structure, and these are like the so-called chemical properties, the angle between hydrogen and oxygen. So these are chemistry, and I don't think I'm going to do so much. In fact, you must have learned it in general chemistry before this, so I'll just skip. So roles of water for plant growth. There are various, and I think I've covered most of them. So I'm going to focus on those that I haven't covered. So let's go one by one. Number one, primary component of photosynthesis. I told you just now. Turgor pressure. Now this one I haven't tell you. Now, turgor pressure is the pressure that is exerted by having enough water inside the plant cell. By having enough water volume, plant cell will maintain its internal pressure and therefore can sustain its uh, integrity of the plants. Let's say, for example, if there is not enough turgor pressure due to the lack of moisture inside a plant cell, it will look like a deflated balloon. So I think you know how the deflated balloon looks like, right? So it's more or less like that way, okay? So if it is deflated, then it will lose its strength and then it will be flattened. Yeah. Now in this case, we don't call it flatten or like whatever, we call it wilting. So wilting is like you have a plant that falls down. So that's wilting lah. Okay. Now apart from that is water also is a solvent for majority of those polar minerals. So as you can see, these are the examples lah. It could be nitrate, ammonium, hydrogen phosphate, all of which are macronutrients. So if you look at the following ones like zinc, manganese, iron, these are trace elements. So whatever the types of this nutrient, whatever the types of these elements, if they're polar, they should be able to dissolve in water. And this is important because only when they are dissolved, then it is possible for plants to absorb them. Plants absorb this nutrient when they dissolve in water. So that is very, very important because if there is not enough water, there's no nutrient for the plants as well. Yeah. Okay, next one, solvent for to move products of photosynthesis through the plant. So this one is like if human got bloods, water or the sap cell or the saps, we call it the saps that contains probably 90% of water, they are also circulating the oxygen, the dissolved gas, like oxygen, carbon dioxide inside the plant as well as the nutrient. So you can say like water, just like human blood, they also flow inside the plants as well. Okay, next one is regulation of stoma opening and closure. So this one, if there is a, now I'm sure you know that the plants, the plant, what is it? The leaves of the plants, they also like exchange gases due to, from through this stoma. So the opening and closing, how do they open and how do they close this so-called stoma is by the changes of water pressure near the stoma. Now, how exactly is that happening? I think I will leave that to the biology lecturers to just explain that. But now you know lah, yeah, most of the movement, okay, whether it's cellular or maybe in macro scale movement, yeah, through the plants, most of them they move due to the changes of turgor pressure. So this probably is related to turgor pressure as well, yeah. Okay, next one is source of pressure to move roots through the soil. So apart from the leaves, apart from the stem of the plants, the root also, so part of the plants, they also move due to the different pressure exerted by different amount of water in the plants. So if the roots wants to extend, then the pressure, the internal pressure have to be increased. So the plants will pump more water possibly into the roots so they can extend. Yeah. And also finally, medium for biochemical reaction. This one is like more very similar like, yeah, to the third point, solvent to move minerals. So only when the minerals are moved, then only the biochemical process can occur. So most of these are like representative of the chemical reactions that happen between the enzymes, the nutrients, and possibly some energy from the radiation. So these are the important parts. Now moving on. Now this is important, yeah. How does water interact and where is the location of this water? Now there are several types of water that we are going to learn today, and number one is adhesion water. Now adhesion water means these are the water that is located on the surface, exactly on the surface of each soil particle. So you can say that no matter how big or small is the soil particle, there will be a thin layer of water that interacts. See? Now they have another word for it, they call it hygroscopic water. Okay. Now why do we call it hygroscopic water? Now if you don't know what is hygroscopic means this kind of water will have a tendency to be highly absorbed by one material. Now I'm not saying that all soil particles are very hygroscopic, but this kind of water, they are called hygroscopic because they have stronger interaction with the soil. Yeah. Like I told you, there are many types, and there are many types of water in the soil. So this one will be held stronger compared to other types of water. Okay. So if you can see right there on the surface, they will be like having the closest interaction with the surface of the soil. Now we still haven't come to the parts or the chapter where we learn the chemical structure of soil. But mind you, on the surface of the soil particle is not spherical, just like this one, as you can see from diagram. It's not spherical, because if you can like magnify, like if you can magnify into microscopic scale or maybe in the nano scale, if you can see the functional group, there are many polar functional group on the surface, uh, like a lot of oxygen, a lot of oxygen with negative charge, with a net negative charge on the surface. I'm not talking about one or two, I'm talking about a series. So if you look at the surface right here, they consist of a lot of negative charge on the surface. Now, because of that, whatever the water molecules that is closest to that will be strongly attracted, okay? Will be strongly attracted by one force called electrical forces. I would rather call it electrostatic attraction. Yeah. Now, most of the chemical bonds, I'm sure you know, covalent bond, ionic bond, hydrogen bond, whatever bonds that form, they will involve some maybe exchange of electron, but this one does not. So if it does not involving sharing of electron or a transferring of electron, so this considered a weaker forces, but still strong. Why we still call it strong, even though it's like a weaker force between them, is because the large amount of a large amount of functional group on the surface of the soil. So they have a lot of functional group, and therefore they held strong. Okay. Now you might have asked me what kind of forces, what kind of electrical forces that operates here. Okay, there are many. Okay. Now, out of many weaker force that we are learning right here or previously in chemistry, the strongest among all of them is hydrogen bond. I'm sure you know what is hydrogen bond. I will not going to explain what is hydrogen bond. If you don't know, maybe you can Google after this in YouTube and learn what is hydrogen bond. Okay. Apart from hydrogen bond is dipole-dipole interaction. Okay. If it's not dipole-dipole interaction, it's possibly dispersion force. Dispersion force is the weakest. Now, no matter what you will have dispersion force. Now, hydrogen bond only exists on a certain condition, in which this condition is met on the surface of the soil. Like I told you, there are many oxygen groups with negative charge, and because of that, water can form strong hydrogen bond. Yeah. Okay, now due to the strong interaction of this hygroscopic water or adhesion water on the surface, they were obviously going to be held tightly. So once this water interacts with the surface of the soil, they don't move anywhere, they're just trapped inside here. And more so, some of this water actually, they are they're also trapped inside the pores, the small pores within the soil particle. So don't look at this particle as it is very solid. In fact, they are probably not solid. If you're talking about organic particles, if they are organic particles, they are full with a lot of small pores, micropores, maybe mesopores. So the smaller those pores, the more likely they will be held inside due to hygroscopic water. Okay. So one more time, what is hygroscopic water? They exist on the surface and they're held tightly by the strong interaction. For example, hydrogen bond. And yeah, just now I told you, if they are like a trap inside the pores, most likely there's an additional right here, which is capillary force. So that adds to the strong bonds, okay, the strong interaction between water and also the internal pores of the soil particle. Next type, okay, so this is the second type of water we call the cohesion water. Now, cohesion water is very different than adhesion. While adhesion while adhesion water interacts with the solid surface, cohesion water attracts between water and another water particle. So this is like liquid with liquid phase. Now, as you can see right here, this is hydrogen bond. So this probably is not really a full charge. This is possibly delta plus partial charge, not really one full charge, maybe less than one. Yeah. So this is delta plus, this is delta minus. And actually, one water molecule have two delta minus, but it is not accurately shown here. But it doesn't matter, because what matters right here is, in order to show cohesion water, hydrogen bond is shown, and compared to adhesion water earlier, there's only one bond with another water molecule. So I ask you, how many bonds? One. How many bonds in adhesion water? More than one. In fact, many, many, many times. So you can say cohesion water weaker than adhesion water. Now, why is that matter? Why is that important? Because earlier, adhesion water is immobile. They cannot be like moved away from the surface of the soil. What does that mean? That means the plant is very likely cannot absorb this water because they were held tightly. However, if you look at cohesion water, they were held loose, at least much less stronger than the adhesion water, and therefore, most likely the water that is absorbed by plants are coming from here, the cohesion water. Yeah. And because of that, if they are not like held tightly, they are more mobile, they can flow, although they are not flow like the one we see flowing very quickly, but they do flow due to forces of capillary and also gravity. Although I say there might be another type of water that is more subjected to gravity, most likely the cohesion water is less held tightly and they are more mobile than adhesion water. Yeah. Okay, now, just now I told you there's another part that affects water movement, which is gravity, right? Okay, now, I know water will flow with gravity. However, when it comes to small pore size, then what is it? Capillary forces takes over, and the gravitational pull will be negligible, which means that water, when it flows into the soil, at one point they seems to be stop flowing, because at certain point inside the soil, the pores get so small that the capillary force actually interacts much stronger than gravity, so they are like virtually stopped or suspended somewhere in the soil. Okay, but I can tell you lah, this gravitational force is more applicable nearer to surface. The reason? Because on the surface, you will find bigger pores, bigger soil pores. And because of that, you have less capillary force, and then they can flow much more freely. And if you want to compare gravitational water versus adhesion water and cohesion water, you can virtually see like gravitational water is the furthest from the surface of the soil, and because of that, they are said to be the least held by the soil particle, in which what makes them move. Gravitational water is subjected by mostly, as the name says itself, gravity. So moving down lah, this kind of water. Okay, so there you go. Three types of water, how they interact, what are the forces that interact and move this kind of water. Basically, you can say lah, there are like surface interaction. Okay, surface interaction due to capillary with capillary force. If there are like bigger pores, then gravity takes over, and then you have these three kinds of names. So students, if you want to study this chapter, you can study lah, because it's without failure lah. Every year exams will ask you this question. Okay, what kind of water? Because why? Because after all, this is what soil is about. We need water for life, and how do we get water? Through this. Okay, and you can start remembering all these names and also how they interact in water. Okay, because why? With three keywords right here, it makes perfect sense to give you one essay question. Although I cannot guarantee you lah, because if I do ask you question like this one, you can tiru, is it? You can refer to notes. So yeah lah, I will give you question right here, but not as easy as you think, not as direct as you think. Yeah. So I'm going to move on to water content. So next one is we're going to learn what kind of ways we can determine, okay, the content or the percentage of water. Now there are two ways you can describe water content in soil. Number one, the easiest way is by weight percentage. So you just calculate lah, what is the weight loss, okay, after drying. Before drying, you weigh it using balance, and after drying, you weigh it again and see what is the difference. Usually the decrease lah, okay, decrease of weight will signify the loss of water. Now, although this is possibly not exactly true, but usually it is a case lah, yeah, because I don't think gas will going to weigh significantly. So assuming lah, most of the weight loss coming from water. By the way, there is another way also that you can determine the water content, which is by volume basis. Now, volume basis is a bit tedious because you possibly need to like determine the volume using gas technique. So usually not many people reporting volumetric percentage lah, yeah, most of them they are gravimetric. So this is the formula, pretty direct. Weight loss, okay, wet mass minus oven dried mass, and then divide by oven dried mass, oven dried mass. Now, okay, this is just one example. Now, even though you use the weight loss to determine the percentage of water, sometimes people might ask you on what basis. Are you determining or using wet basis or dry basis? Now, from what the formula is shown to you right now, this is called dry weight basis. Okay, so this is the water content by dry weight basis. Because why? You look at how do they calculate the ratio. So they are determining the water content against the dry mass. Sometimes lah, due to the research, okay, due to the demand of research, some scientists might determine the water content based on wet basis. Okay, so I'm going to run a bit away lah from the soil moisture. Now, some soil moisture, most lah, I would say most soil moisture, we're going to determine the water content through dry basis because I don't think there is any problem, right? However, if you look at the food industry, okay, for example, those people that works in Jabatan Kimia looking at the food safety, most of the time they're using wet basis. Because why? You go to pasar, you buy sayur, okay? They want to determine the so for example, heavy metal content in a vegetable. Do you think people are going to try to buy dry vegetable or wet vegetable? So I think that answers the question, right? Because in some cases lah, it is not realistic to use dry weight. Okay, so food industry is just one lah, yeah. They will usually use water content on weight basis, whereas in soil, it's a little bit of both, yeah. So sometimes you can see in research people use dry basis or wet basis, but I think this is pretty straightforward lah, yeah. If you were given this question, however, I can guarantee you won't lah. This is too easy for you. I mean, this is secondary level school children's question. Anyway, this is more likely. Okay, now once you have determined the water content, dry weight basis or wet weight basis, you can actually use that. And if you know what is a bulk density, you can convert the water content from weight basis into volume basis simply by using this formula. So you can see right here, if you know what is the percentage of water on weight basis, you just multiply with the bulk density, divide by water density, which is 1. Why? Because water density 1 gram per ml. Then you factor in lah. So make sure the unit is correct. Then you should get the water content in volume basis. Okay. So two formulas, yeah, two formulas you see in here. I don't think you're going to see any question that asks you to calculate. You can find it in any textbook that you want to find. If you want to test yourself, you also can test yourself from the past year final exam questions. So the exercise is on your own. It's on your own. You want to try, you try. If you want to score A in examination, you better try. Final exam question from past year. You try yourself. I won't going to drill you up because why? Too easy. I don't think you need drills. You just need to spend some time diligently, test yourself against a final exam question from past years, and then you should be good enough. Yeah, should be good enough. Oh, by the way, there's one more thing I forgot. After this, you next experiment. Yeah, in your next experiment, if not mistaken, experiment 5 and 6 involving this one, soil moisture, soil organic carbon. So you will going to go to those and use this formula. Most likely you're going to use these two formula to determine moisture content. So I would say that is the only exercise that you have lah through your lab report. So make it work, yeah. So okay, now calculation done. Now what next? We have a term that we need to get familiar first lah. Yeah. So there's a word called water holding capacity. So what is that? That means the amount of water that can be retained by a soil. Okay. Now, most likely this water holding capacity, we are going to call it field capacity as well. So, what does that mean? Still, what does that mean? Some people might not know. Okay lah, water can absorb water. Soil can absorb water and they can retain it. But my question is, what kind of water that is retained by soil? Do you still remember the three types of water earlier? Okay. So I told you earlier, the one that held strongly by the soil. What is it? Adhesion water, kan? Okay. Adhesion water or the other name hygroscopic water. So this will be com confirm lah. Confirm. This water will be trapped inside because it's strongly bound to the water. And possibly there might be some cohesion water, depending on the capillary force that a soil may have. So how big is the pore size determines that. Because if the pore is too big, they may have a little bit more of gravitational water, and what happened to this? It will be pulled down by gravity. So can we say this is retained by soil? Possibly not. So by saying water that is retained by soil, we're essentially talking about two types of water here: hygroscopic water and most likely cohesion water as well. Yeah. So when we say it is retained by water, mostly is due to capillary force and also surface interaction with water. Yeah. So a lot of relation to what we have learned earlier, and one thing that I need to remind you lah, soil is not the same no matter where you go. They may not be the same. Why they're not the same? Because some soil may not have the same composition in terms of clay, silt, and sand. They may be different in those composition, and hence you have different texture. And because of that, also you may also have different water holding capacity. Okay, that's number one. From the different composition of mineral phase, because soil also will have another component, which is the organic phase. Now, organic traps water very differently than mineral. Yeah. So it is said, whatever soil that you have, if the soil is containing more clay, if they contain more clay or more organic matter, that soil will going to have very high water holding capacity. Okay. So I think I will try and see what is the other slide that can tells you. So I think to begin with, we're going to discuss about how water interacts with the soil particles. So as you can see right here, there are like 7 particles of the soil, and there are like many waters that interact between them. So as I told you earlier, where is hygroscopic water? Exactly on the surface. Yeah, very near to the surface. They cannot go too far away. Yeah, and these are the soil, and these are the water that tightly held on the surface. Now there are other types of water which is capillary water, as you can see right there. If they are like nearer to the gaps or the pores between two particles, if they are not too big, capillary force we're going to trap them. Therefore, they call it capillary water. If they go to a bigger pores, then air might goes in, and if they have water, they won't last for too long because gravity will pull them down. So this is why, okay, this is why clay has a lot of water. Because why? Clay, they have many of these small particles that majority of those water, they are trapped through hygroscopic water. Do they have capillary water? Maybe, but very unlikely because those soil particles, we're talking about uh, micro scale and even nano scale, so small that gravitational water possibly do not exist. Majority is hygroscopic water and also capillary water, some. Yeah. So that's why clay have high moisture content compared to other types of soil like silt and sand. Okay, so what affects water holding capacity? As I told you earlier, the finer the soil particle, the higher water holding capacity, like clay. Clay is higher than sand. Yeah. And there is another reason also that determines the water holding capacity. Now, clay itself also may not be the same. Some clay, they can absorb more water, some cannot. Now, such is evident lah, as you can see right here. Examples such as montmorillonite and also vermiculite. Now, these two are clay. One is available in Malaysia, the other one not so because of the way that they're formed. Now, those that you can see from the layering bukit, yeah, once the side of the hill, the red soil, most of the time it is montmorillonite, and these are the clay that interacts strongly with water. So after an event of heavy rainfall, you can see the rainwater full with kelada, isn't it? All those murky water. Those are due to the suspension of this clay lah, montmorillonite. They interact and then they are suspended. It takes days lah in order for them to settle down. Vermiculite is formed by some volcanic interaction. So these two clays, okay, these two clays are particularly important because they can expand, because they can absorb a lot of water, and they can also trap nutrient with water coming into them lah. The only thing, this problem of these two is that it might be part of the erosion process lah. Yeah, the erosion process that contaminate the water bodies. But in terms of soil, they're very good. They're very good in trapping water and also nutrient. Now, the other types of clay, you can see kaolinite and goethite. Kaolinite and goethite, they are very different in a way that they completely opposite of montmorillonite. While montmorillonite and vermiculite absorbs a lot of water, kaolinite do not absorb water. They mix well, but they do not absorb too much water, and because of that, they don't swell. They don't swell and they don't simply detach from the soil unless you mix them up lah. And then, so when kaolinite is flooded with water, no problem. It stays the way it is. However, if montmorillonite is flooded, it will expand and then it will disperse. Kaolinite do not expand and do not disperse. And because of that, kaolinite usually have lower water content, but that is good. You know why? Because most of those tembikar, most of those ceramic ware that you can buy from supermarket, the white color one, now this one they are made from kaolinite because they don't expand. When it is molded into shape and then burned at high temperature, kaolinite actually will going to stay the same before it is heated, and it is said to like be able to uh, merge and then interact with another clay particles during heating to form a very fine structure ceramic ware. So that is why kaolinite, they're so good in this case. Most of the time kaolinite is used for making pottery or potware, pottery or ceramic ware. Yeah. Okay, now another factor lah that affects the water content is the organic matter. Like I said, it interacts very differently because compared to clay, organic matter is very light, low density, very low density. However, in terms of functional group, they are more or less the same. And because of that, organic matter is even better. One of the best components in the soil, which one is the best that absorbs water, is actually organic matter, not clay. Clay can absorb a lot of water, but it's not the way that we hope for. Because if you can have more organic matter, that should be the best way for the health of the soil. Because organic matter can absorb water, obviously. But there's another thing. It will going to preserve the nutrient content. Because why? Organic matter itself is a nutrient. So it's like you have nutrient, you have water, best condition for photosynthesis of plants lah, yeah. So there you go. These are the factors that affects water content. You can have clay, more water, more organic matter, more water content as well. Yeah. So I told you just now, field capacity. So field capacity is just one condition out of these three that describe the content of water in the soil. So the other two is saturation. The name tells you full of something. Of course, this case, full of water. Wilting point is the point where the plant starts to wilt. That means not enough water. So based on these three conditions, you can possibly guess lah, yeah, how much water is trapped inside the soil. Yeah. Now this diagram perfectly shows you the content of water. The more blue color region, the more water content. Now I believe that the soil particles remain the same. At least it looks quite the same to me. And also the name associated to the water content. Now, I want you to look at saturation. So if you look at saturation, it is said that no space, there's no air space within the bodies of the soil. All of those pores are filled with water to the point that water starts falling down. So in saturation, no matter how big is your pore, micropore, mesopore, or macropore, everything filled with water. And because of that, you have macropore. Remember, macropore is very big, and therefore they will have gravitational water. And gravitational water is not held strongly by capillary force, and therefore they fall down. So usually at saturation, you have all types of water: adhesion water, cohesion water, plus gravitational water. So in reality, is this possible? The answer is yes, but maybe after rainfall. After a heavy rain, then you will see this condition. That's why lah, yeah. That's why in soil sampling, procedure, there are conditions. Before you go and do soil sampling, there is a condition in which there should be no rainfall a day or 2 days before your sampling trip. If the day where you want to go for field trips to collect soil sample, that day it starts to rain, most likely your soil will be in saturation state. Too much water, it does not represent the true capacity, the true water holding capacity. Yeah? So which one is true then? The middle one, yeah. So this one is said to be the true water holding capacity that can last a bit longer. We call it field capacity. And then, like I say to you, field capacity may be different based on different soil texture and also different content of organic matter. But what you can see right here is the one that is retained, those water that retain. So you can say under field capacity, there should be very minimal gravitational water, very minimal. Yeah. So frankly speaking yeah, the lab report that you have submitted earlier, during the first experiment, that is not really an experiment. It's actually the technique where you collect soil sample and then you prepare it. So if not mistaken, during inside that lab manual, they ask you to put it inside the oven, then dry at certain temperature at certain time and take it out. Now, To tell you the truth, that technique is actually you only use it when you're running out of time preparing soil sample or whatever. Because usually the preparation of soil is once you have taken the soil sample from the field and bring it back to the lab, you're going to isolate the debris, maybe the large soil and stone particles from the soil. Then only, according to lab manual, you put it inside the oven. But actually, you don't need to. You just put it with under sunshade. You can put it under sunshade and then let it dry by itself. We call it air drying. Yeah. So the preparation, the soil treatment before you do any kind of experiment, whatever, pH, soil texture, or whatever. The best way, okay, the usual way to prepare soil is just simply put it under shade, let it dry by itself, for maybe 3 days. Yeah, 3 days after sunshade, then your soil is ready for analysis. Because after air drying, whatever the gravitational water will be dropped down. Okay. Now there might be some evaporation coming from the cohesion water, but it's unlikely, yeah? It's unlikely. So most of this field capacity only contains two types of water: adhesion water for sure, and then cohesion water. Yeah. So that is field capacity. Now what about wilting point? Now wilting point is when the point where the plant starts to wilt. That means plants cannot absorb water. So I think I've told you earlier, which type of water that can be absorbed by plants? Cohesion water, remember? Yeah. If the plant starts to wilt at wilting point, that means this condition maybe have very minimal content of cohesion water. Don't mention about gravitational water lah. So you can see like gravitational water maybe does not exist anymore. And even cohesion water is at a very minimal point that the plants cannot absorb. Now, because plant cannot absorb, then they wilt. So you can say like at wilting point, if you can still find water, most likely this water will be adhesion water. Remember the adhesion water that's strongly attached to the surface. Yeah, you may still find some adhesion water near the surface of the soil or maybe inside the pores. So there you go. Different conditions of the soil, different types of water contained in these three conditions, and how they interact. Okay, so I'm probably going to give a few or two questions based on this because this is too easy. I will let you score, but you would have to understand like, yeah, how it works. So the whole thing, or the whole thing of like water content, the condition is all described in this diagram. Yeah. So I think, oh, I jumped. Now these are the description lah, yeah, description about saturation, excess water, field capacity, wilting point. I think I jumped a little bit and I told you all about these 3 points. So I think you can read by yourself lah, yeah, you read yourself of this description. I don't think I'm going to like explain all of it, but the points are still here. So you read it lah. And these are the examples of different soil texture and also their field capacity. As you can see, clay has the highest field capacity because clay, they're so small. They have a lot of cohesion water as well as adhesion water. They may not have too much of gravitational water because that's no need lah, because they have a lot already from the adhesion and cohesion water. Yeah. And again, this diagram is very similar to what I have described to you earlier. So I think very much the same point. Okay, now before I move to soil movement, let me conclude lah, yeah? Let me conclude. Um, What do you need to study for your test and examination are this diagram. I think there are like three diagrams already shown to you that describe the three conditions and the types of water that contains in these three conditions, and also the interactions that involve. There are many things that get around. So if you want to ask me how many marks, if I want to give question from here, that will be 9 marks. A lot of marks given here. Okay, so if you want to study, this is what you should know. Yeah. The conditions, the types of water, and also the interactions between these water and also possibly the surface of the soil. Okay, so mark it down. If you want to study hard on this one. This is what you should know. Okay. Now, water movement is equally important as the water content itself, because as we know, water does not stay immobile or stagnant, because there are many forces and many interactions that can move the water content. So either by gravity, if gravity goes down, if it's capillary, it depends how does the capillary force is exerted. So after this, we're going to talk a little bit more on how those capillary force are involved, and there are two more. There are two more factors that can also move water. I'm sure you know what is osmosis. So if the soil in for some reason may have some salt content higher on one part, so the parts where there are high salt content, they will have osmosis and they absorb a little bit of water. So some parts they are having more water because of that. And there is another factor when you have sunlight. Okay, when you have sunlight, you have higher temperature. Water might move up, might rise up due to evaporation. So there are many ways that water can move inside the soil. However, after this, we're going to talk a little bit more on the capillary force. Yeah. So there are like two main forces that we're going to talk about here: capillary force and also gravity. So like I told you, gravity moves down. Capillary, it depends. Yeah, it can move up, down, sideways, left or right. It is possible under capillary force. Yeah. Now, how does it? How does the capillary force can move water? They can due to the force that like pulls within the soil particle due to the existence of capillary. Now, if you have one part of the soil that is very porous, maybe the water might go into flow and trap there more often if they're like larger pores. So it depends. It actually depends. Yeah, there's no way you can predict one way or the other how water movement can go to, because one apart from the pore, it also depends on the water content. Yeah. So gravity is more predictable because gravity force only goes down to the earth, so water pulls it down. However, if in the soil, which is very pretty normal, in the soil, you can find horizons. Okay, horizons that is impermeable by water. Instead of flowing down, they either stop or they float sideways. Yeah. So if they stop on a layer that is impermeable, they start flowing sideways and then go to any parts where there are like some areas that is permeable, so they can keep flowing down. If they don't flow down, then they flow horizontally. That is how underground river is formed. So now here's the philosophy that we scientists usually use, soil scientists use, in which the movement of water is held by the energy. Okay, it is due to the difference of energy in which substance will flow from a state of high energy to a state of low energy. So that is the so-called the physics philosophy behind this one. Um, how does it work? So it works through the water potential. Now, say if in this case the tension of water, yeah, the tension of water is equivalent to the opposite direction of pressure. So in normal system, usually the system will tend to relieve the pressure of this entire system. Okay, so the soil potential, the description for that is, as you can see right there, amount of work that must be done per unit quantity of water in order to transport a quantity of water from pool or pure water to the soil water. Now you might be asking me, what does that mean? Well, that means this is how water relieves its pressure and flows to one direction to the other. Quite difficult to understand, kan? Okay, don't worry, let's look at the next slide. Okay, I think this is possibly more easier to understand, kan? So this is water potential, okay, in which the water potential is equivalent to two more potential, the matrix potential, which possibly can be due to the porosity of soil. Um, so more porous, they absorb more water, less porous, less water. Or one more factor, sorry, three factors right here, not two potential, three potentials. One is matrix potential due to the nature or the physical properties of the soil. The next one is gravitational potential, which is, as you can see, gravity pulls it downwards. And one more, osmotic salts. If you have more salts, they can absorb more water. So where is those salt? Depends. If it moves, I mean, if it's next to the source of water, it moves sideways. Like if it's under the soil, then it moves downward together alongside with gravity. So there are many ways that water can move due to this different potential. Yeah, and the value of this potential is always negative. If it's like the highest potential, it will just be zero. Zero is the highest value for water potential, and then it will decrease downwards from -5, minus single digit. It could be up to like -100. So you can say like between 0 to 100. The round numbers that you can see right here is always negative. The more negative of this soil water potential, okay, the more the drier the condition. Yeah. Now, I think the diagram shows you everything. Like if it's wet, if it is saturated, it is said that the water potential is at zero value. If it's very dry, very dry, maybe 100, -100. Of course, if you ask me, do they have unit? I would say yes, they will have unit. But for the sake of you understanding how does a condition looks like, so these are the conditions. Wet is 0, dry is minus, always minus. Maybe the highest is -100. So what does that have to do with the movement of water? You see, water will move from a direction to a direction where it is lack of water. Now, if you have a lot of water in one place, that will going to build some tension. Okay? Tension in terms of having too much water. So as you can see right there, physics. Yeah, I'm not going to tell you too much about physics, lah, but let's learn about the philosophy. How does water work? How does water flow? Okay? Water tends to flow to the direction from a region which is more water to a region which has less water. Now you can see right here in the river banks, like for example, if you have like in a saturation state, it's 0 bar. In terms of water potential, is 0 bar. It will tends to flow to a direction where it is very dry. Now, of course, just now you've learned if it's very dry, it will always have a minus value potential. So usually this is how they flow through from wet to dry, from a potential which is 0 to a potential which is negative value. Okay, now actually kan is and also calculation involved. If you have friends like in civil engineering, or maybe I think civil engineering, because they learn hydraulics, they will require to learn how to calculate this potential. So consider yourself lucky lah. Under this subject, soil subject, is just enough for you to learn lah the concept of water movement, what causes water potential that causes it, from what direction lah. Usually the question will be involved from wet region to dry region. Usually it will flow through due to various interaction. Yeah. So I think from here I will just going to show you one more time this like so-called the scale, I would say. Okay, the scale of this water potential alongside with is soil water classification. So just now we've learned there are a lot of condition, soil water condition, starting from the highest water content, the saturated condition. That state will have the highest amount of water, wet, so wet that gravitational water may flows down. Yeah. So in that condition, you can say the potential is at 0 bar. If it's very, very dry, it's air dry lah, yeah. Air dry is a condition where you have minus 100. If it's oven dry can be said close to no water inside, not even hygroscopic water. That condition, the potential is minus 10,000 possibly. I don't know the exact value, but you can see lah, yeah, the difference, the scale of the water potential, and it's paired to the different conditions. Now, you don't have to worry about the numbers lah, yeah. I won't going to ask you what is the water potential in bars if a soil is oven dried. Possibly not. Because the point where we are here today is that we're going to learn the potential lah, yeah. What is the highest value? 0 only. The lowest value could be extend to minus 10,000. But the most important thing is the terms. The terms where you can see in the scale: saturated, field capacity, wilt point, air dry, oven dry. These are the things that you need to understand. Okay, first, how much of water content, okay, and then agak-agak lah, yeah, approximately, what is the potential? So you know lah, saturated is always 0 kan? Saturated is always 0. That's very predictable. And then you move down onwards. Okay, so these are the things that you need to know lah. No need to go and memorize every single word in this slide. No. Like I said, I want you, it is compulsory for you to learn the states of water, what types of water. So the so-called water potential is just part of it. And then the most important part that you need to know is like, where does the water flows through? Yeah, that is even more important. Yeah? So these are the potential in 1 bar, and also this is mostly like a pressure use. Bar also uses this. The pressure also uses a bar unit, kilopascal. So this is more towards like the pressure. Now this pressure is built to the high water content lah, yeah. Uh, that is why I told you just now that it will going to move from a potential from 0 to a more negative potential, because with less potential, that means the pressure will build and going to relieve its pressure by water flowing to a region which have less pressure or less water potential. So more negative value in water potential. Now in this case, usually it will going to detect the direction. If you can find an area which is more wet, will likely flows to an area which is drier. So in terms of the energy level, it will tends to flow from high energy, okay, to low energy. Low energy is those soil that is drier. Yeah, I think this diagram will shows you that lah. Now, you can say that the drier region is either on the roots and also on the surface of soil. Now, now sometimes when we say dry, doesn't mean that it is dry by high temperature. No, although most of the case it is. Now, for these two examples, the reason why root is said to be drier is because root, I'm talking about living plant root, they absorb moisture. I'm sure you know why. Because it needs water for photosynthesis. So water is kept being removed from its surface upwards for photosynthesis. That is why the surface of root is said to be drier, because there's a constant loss of water upwards due to photosynthesis. What about soil? Quite strange, eh? Soil also very dry, minus 70. -7 in terms of water potential. Why is that so? Now, you have to remember in soil, it's not just soil, because microorganism might colonize this soil. And for your information, uh, some of these microorganisms might also absorb water for various reasons. It's like a microorganism that can do photosynthesis. They also can absorb water and have their own photosynthesis. But most of this water, they are being used by microorganisms like bacteria. They also use water for their own consumption. So which is why, okay, areas where there are like living organism that uses water, they say to be dry. Now, what about in between? So in between here depends lah, yeah. So most likely you can find water from this region which is further away from living organisms. So they are said to be having a higher, not high, higher water potential. So you can see here, this is said to be higher because why? If you put a negative sign, so this is very high, the highest lah among this water potential value. So that is why water will flow from a high water potential. Wait, this is like from area of low water potential. Wait, the term seems like it's the opposite of what we are seeing right here. High water potential is negative value. Okay, so a little bit of confusion right here. Which one is high, which one is low? So according to the text right here, written right here, it is said to be more negative. If the water potential is more negative, they are calling it as high water potential. Okay, so uh, I still think that this area with a low potential, with a less negative value, having a higher tension. So they go to a place with lower water tension, and in these two places, the roots and also the soil, they have high water potential because the numbers is bigger lah. Yeah. Sometimes it's quite confusing looking at these numbers, but I mean, you know the idea. Like earlier when I said, where does water flows to? It flows from an area with more water to an area which it has less water. I think that does not change, like, yeah. But one thing that I hope you don't confuse, like I did just now, is that which one is high water potential, which one is low water potential, as it says. The value, if it's higher, it's said to be high water potential, and vice versa. Anyway, I have to be frank with you, like, yeah, this diagram, I've used it before in final exam. So the student, some can answer, some cannot. This is direct. You can open your book, you can refer to it. But well, if you see such a question, then consider yourself lucky lah, because this is like a direct question. Very rarely this one can be used to ask an applied question. If it can give you a calculation question, I would love to do it, because only that way that you won't be able to tiru lah and copy. I mean, get your answers from your textbook, from your internet. You can only like count and determine the answer. But this is not what it is in this subject. Yeah, in this chapter, I can assure you lah. Yeah, apart from the question that asks you to calculate water content, beyond that, you possibly don't see any more questions that they ask you to calculate. Yeah, but actually there is. Yeah? There is a way where we calculate water potential and predict the water movement. Yeah? And this is one diagram that you can use. Yeah. So things like this, like, yeah. Okay. So next part is we're going to determine, like, yeah, what is uh, the factors. See? Yeah, the factors that influence the flow of water. Pore size. Here they say pore size is the most important, and I also agree, because pore size, if it's very small, usually it is hygroscopic. They will tend to draw water if it's very, very small, because like I told you earlier, if they have a very small particle size, a very small pore size, there will be strong capillary force. So they tends to absorb water from somewhere that have free flow water like adhesion water. So adhesion water can move, and they move into small pores with capillary where they were like immobile, or they stop flowing due to the strong force. And I repeat myself here again, yeah. Two forces that allows the water to move: gravitational water, due to gravity, they move downwards all the time. Capillary force, all direction, can move down, can move up or sideways, depending on where is the water potential, the difference in water potential, then they will move accordingly. So gravitational and capillary force act simultaneously. So there's no cases that they act differently, because in nature gravity will always be there. The only question is whether capillary force is strong enough to be like significant. Yeah. So back to the question again, is the soil particle or the pores small enough? If it is small enough, then you possibly can see a little bit of capillary force interacting. Yeah. So back again, capillary force, cohesion water. So adhesion water also will be there as well. So cohesion water maybe a bit more if you have a larger pores. So basically it's the same that what we have discussed earlier. Okay, because of that, then I'll skip lah. Yeah, I mean these are the same points that we have discussed earlier. So yeah, sandy soil, they are quite large. They have a lot bigger gap compared to clay. What does that mean? That means they are majority having large pores or macropore, in which uh, the capillary force may not be as significant. And because of that, most of those water, they are gravitational water, which it is, flows down the moment you water it. And this is how they interact in soil. Yeah. Okay, now next 3 points: soil, sandy soil, texture. Okay, I will skip sandy soil part because I've already explained that. Now, number 6, factors that affect water movement through soil include texture, structure, organic matter, and bulk density. Again, already explained, so I'll skip. Number 7, the rate and direction of water moving through soil is also affected by soil layers of different materials. So yeah, just now I told you again, in the soil horizon, at some point you will have a layer of impermeable soil, which is what I told you earlier lah. This one, if they're impermeable, they cannot pass through. So what? Then they flow sideways. Flow to sideways with lower incline along the slope. So they go to a spot where the soil is no longer impervious, so they flow down. Yeah, that is if we're talking about gravitational water line that is like pulled down by gravitational force. Okay, I think this one is last slide. I won't going to explain this one because this is the formula used to calculate water budget, and this is particularly important, especially nowadays. Like, yeah. Wait a minute, is this the last slide? No, last two. Yeah, last 3 slide. Now I want to elaborate a little bit further, like, because this one is related to another subject, which is water resource technology. Now, under that subject, majority of discussion are revolving around surface water. However, the soil itself may contain some pool of water, some reservoir, we call it, and that is where you get your mineral water from the soil. So they pump it up, filter it, disinfect it, that becomes your mineral water. Uh, but there we have again, due to the high pollution, now even surface water also having trouble giving us clean water. So you can imagine the soil, what happened to the soil? The soil actually is more subjected to pollution, yeah, for various reasons, yeah. And it also depends on the location as well. If it is highly urbanized, then it will be dirty. However, if you're talking about the source of mineral water, usually they're quite clean lah, deep inside the forest or maybe away from the source of pollution. uh, because the moisture inside the soil will not stay stagnant. If it is, it's due to the capillary force. Majority of the water will flows down due to gravity, and until that, at one point they are trapped into impermeable region, and then they stop there inside there, which is a reservoir. Now, talking back on the water resource technology, the reason why we are here is because in some point groundwater can be a source of water for human application. Previously, you have a lot of tube well. In bahasa Melayu, you call it perigi. These were the main source previously, before all those urbanization, quite clean lah kan. Until Malaysia at one point we are facing with some boom in mining, tin mining. That time, if you can go back to time, that time, there were many incidents of skin cancer. That time, see, with the booming of tin mining, because everybody was using tube well then, and then suddenly there's a pollution in soil due to mining. All groundwater has been contaminated with arsenic. So if there's any clearing of forests or is there any mining activity, groundwater will be polluted with arsenic. And this is a natural process because the moment you open the soil, there's oxidation, arsenic will start coming out. Okay, will start leach out from the soil and ends up in your groundwater, which is why until today, if you are staying in kampong which have less pollution, then possibly is safe. But nowadays lah, not many people in Malaysia, not many state government in Malaysia uses groundwater. Although at some point, Kelantan lah is the highest one that uses a lot of groundwater. Now that is the reason why we're here. Now the region that uses a lot of groundwater, you can see lah a lot of extraction. So this water will going to flow down. Then what happened? Water table, this one, as you can see right here, the water, the surface of water, this is water table. If there too much of extraction of groundwater, what will going to happen to the soil? Not many people realize that if the water has been drawn away, the soil will going to sink. They were going to fall down. We call this phenomena subsidence. If you have a friend in civil engineering, they will tell you lah, yeah, this is one of the challenge lah in civil engineering. Because soil, sometimes they are very soft. They are soft because they have water. So the solution, pump out the water. After they pump out water, there's a hole, a big hole. It happens before in Bukit Bintang. So what I want to say here is that even in soil, moisture content has to be maintained, not like simply you can extract those water. Yeah. So although water can be used, it is not meant to be overused. Okay. So maintaining water content in the soil will also maintain its health, not only for agriculture, but also for the well-being of humans or animals who use it. Because if you extract too much of groundwater, soil will going to fall down, subsidence, and then those water may not be of high quality. Usually groundwater is salty. They're not acidic, they're salty. Yeah. And more so due to urbanization, groundwater also has high pollution level. So that is why in Malaysia, it's not likely that we're going to use groundwater. And I think this diagram, you must have seen it before, water resource technology, that tells you what is a water cycle. So what is not here, possibly less emphasized, is this one, groundwater flow. Yeah. So when you have water that falls down, they percolate inside, they sink through to gravitational forces, and then they flows alongside and into the ocean. So water is actually part of the groundwater or soil water is very much part of this cycle. It's just maybe slower or not apparent. Okay, so this part I will not going to explain to you, and I believe we are at the end of our lecture.